Good afternoon, everyone. My name is David, and my coworker Sanjeev and I today is going to talk about the ZFS diff optimization and also some problems that we fixed. Yeah. So what is ZFS diff is for? So ZFS diff. So for example, if you have two snapshots, you can do a ZFS diff on those two snapshots, and it will show like all the changes made between those two snapshots. So for example, if you look at the below, there's a sample output here. So yeah, it shows that some files are added, some files are modified, some files are like removed or renamed. Yeah. So we use ZFS diff to allow like third-party software to do incremental backup. So basically, we send this information to third-party software, and it will do the copying the files, modified files for backup. So yeah, so it works pretty well for small set of changes. But we found out that there's some problem with if you have a large number of files of changes between snapshots. The ZFS diff will take a very long time. It's very slow. For example, we have a case that we have like 1 million files, 1 million changed files in directory, and it takes like about an hour. So we try to dig where the performance bottleneck is. So we found out that it is mainly in the deno to path translation. That's where that most times are taken. So another issue where we found out is when you have hard link changes mixed in, it will actually break ZFS, break the diff. For example, if you have a file called the file.6 and you create a hard link in another directory, and then you remove the new link you just created, and then you do a ZFS diff, it will show here that the file.6 is removed, but you don't actually remove that file. So the file is still there, but the ZFS diff show that the file is removed. So that's not a correct, not really a correct result that we're expecting. So yeah, so this issue has been reported on GitHub before. Some people may see like unable to determine path or stats for object 107, some message like this. Yeah, so yeah, this is something you might also see before. Next slide, please. Yeah, so how does ZFS diff do the path translation? So because deno itself doesn't store the file name, so it only stores the parent ID. So how it find out the path name is it goes to the parent directory, and it does a linear search inside the parent directory, and in trying to find a matching object ID. So for example, if you look at the graph below, so we have a file called Bob, and its object ID is 108, and parent is 99. So it go visit the parent directory 99, and is do a linear search in the hash table So it find out that, okay, here there's an entry with ID 118, and the name of the entry is Bob. So here it figure out that the file name is Bob. Yeah. So this operation, it needs to repeat all the process all the way to the root directory, so it can figure out like the file name, the directory name of the parent, and then directory name of the grandparent, and so forth. Yeah. Next slide, please. Yeah. So yeah, so because of the linear search, so each path components will cause a big O(n). So if you times like how many layers of your file is, so it's going to add up a lot. And also, if you have a lot of files are inside the common directory, you will also repeatedly doing the translation for those common directory as well. So so basically you're doing the same, you're doing the same thing like multiple times. So if we can cache the result for the common directories, so it will also speed things up significantly. Also the linear search, because when you do linear search through a large directory, you also caching a lot of caches in the arc, so you're like causing unwanted churns. Yeah, so basically, yeah, with a large number of changed files, this problem will significantly increase the total runtime of the ZFS diff. Next slide, please. Yeah, the second problem is the Hardlink problem. So so because we only store like one parent ID inside the dnode, so when we create a Hardlink, so what the current code does is that, for example, if you look at the graph, so we have the file that's in directory ID 5. So if you do a hard link to directory ID 6, so now you have two directory point to the same file. What it does is that ZFS current code does is that it always changes the parent ID stored in the dnode to the new new parent, the new hard link you created. So now when you remove the hard link 6, so you'll find out that because the parent ID stored on the dnode is still 6, so it basically couldn't figure out the real parent now. So that's why it broke the path translation. Yeah, so that's the issue with hard links. Next slide, please. Yeah, so the rest I'll hand over to Sanjeev.
Thanks, David. So like David explained on how we have this issue of sequential search, I think one of the key things that I would like to add to what David said is the ZAP entries themselves are indexed using the name of the file or a directory, and so that's your key. The name is the key, whereas the value is the inode number, and hence you cannot, although it's an indexed search, but it's indexed for the name and not for the inode or the dnode that we are looking for. So that's where the reverse name lookup sort of becomes a problem, because you're doing a sequential search. So the way we try to address this is when you add an entry to the ZAP, we actually compute the hash. So we know the hash value when we are adding it. So what we thought was we picked up that hash and added it to the D node. The hash itself is 64-bit, so we could just easily add it to the D node. And we felt that the system attributes themselves actually lend pretty neatly to this usage. So we added a new system attribute called Z hash value in the D node. Now this brings in some challenges. One of the things is in rename, you would need to update the link name hash because the hash value itself could change. In addition, the parent directory also could change, but that's all right. I mean, the cost of that is not much because you would anyway need to change the M time and C times of the D node. So that's all right. So that was one change that we did. So that sort of addressed the problem of sequential search. And this now reduces to constant time search because once you have the hash value, you could directly do a lookup in the ZAP. You have the parent ID and you have the hash. So it's a quick, it's a constant time cost to look up into the ZAP. So that was one solution. Second, so here is a sample that we have from the ZDB output. We have the object 128 whose parent is 2, and we do have the link name hash for it stored. So what you could now technically do is in the ZAP D node 2, you could quickly look for this hash and the code itself lends it pretty neatly. You could pass in a hint. So we added that part and we can now do a constant time lookup. For the hard links, slightly a longer solution because what we technically need is a way to store multiple pairs of parent D node and link name hash. So storing this is not, depending on how many hard links are created, you'd need a larger space. So initially we explored option of storing it in the D node itself, but the D node, in our case, we are using the standard D node, which is the 512 byte, and there's not enough space there to store. So what we decided to do was add a new ZAP object, and this is allocated only if the file is hard linked, as in if its link count is greater than 1. So only in such cases you would have a ZAP D node allocated, and in that ZAP, what you do is keep a pair of these parent D node and link name hash. So it's essentially a list of those, and we'll quickly see how that looks like. And once you do this, now it's easy because you have the entire list of parent directories that are pointing to this file and the corresponding link hash value. So you can easily list out the various files that are or various directory entries that are pointing to this particular D node. So and the ZFS diff itself right now it lists out the first entry that's found, but you can play around with it. So we actually added a utility which can list the various entries. So we'll get to that in a bit. So if you see here, we have an example where object 5 is actually a hard link and it has multiple links on it. In this case, there are 2 links that are pointing to it. So it has a a parent ID which is 256 that's pointing to it, and we have a link ZAP 384, and in the link ZAP there's the second entry which is 259 which is pointing to it. And the other output that you see here, which is the link ZAP output, it's listing both the one which is present in the D node itself, that's 256, and the second one, which is 259. So you can technically list all the hard links that are referring to this D node. So those are the 2 changes that we did with respect to the Ondisk part. Moving on, we did some additional optimizations in there, which is like earlier mentioned, the top level directories, which are common as you grow closer to the root of the data set, those would be dereferenced a large number of times, depending on how many entries have changed. For example, if you look at the below change here, if there were 200 changed files, we would be dereferencing the directory A, B multiple times in there. Or for example, C itself would be dereferenced about 100 times. So the benefit of caching C is high, and the benefit of caching B is even higher. Or for that matter, benefit of caching A is really high because it's at the top of the tree there. So the benefits actually go up. So what we did was we built a cache in the user land. Now, just a note to remember here, we are not using the standard ZFS diff. Instead, we hooked into libZFS where we are using this. But the same can be applied to standard libZFS as well. We could probably build a cache there. So the other changes that we did is, in order to utilize this, we modified the IOCL that does the denote to path translation. So we pass a flag in saying don't translate the entire path, just fetch us the name, and that's sufficient. So once you just fetch the name, and by the way, because we of the earlier change of link name hash, the fetch is quick, it's constant time. And once you fetch it, and if you know it's a directory, you just stash it into a cache. Files you don't need to, because files would just be looked up once, you don't need them. But directories, you just stash them into a cache, and the next time around, if you want to walk up the path, you could just refer it from the cache and use it. So that's the additional change. So what did this fetch us? Or rather, before we get to that, the summary of changes is in here, but what did it really fetch us? So initial implementation was in Python, which was fairly simple to get it going. And it reduced the time from 60 minutes to about, I think about 15 minutes or 10 minutes. And then we started hitting Python issues. So we stripped that away, and then we switched to C++, and it has come down to about 15 to 20 seconds. Even if we say it's about 30 seconds, from 40 minutes to 30 seconds is a huge reduction. And this is right now shipped. It's part of our backup APIs that we provide to Haiku, NetBackup, and other vendors. And it's running on customer machines right now. So fairly tested and running. So it's sort of tested in there. What effort does it take for us to move it into the community? So the summary of changes that we have done, there are 2 system attributes that we have added that I think is easily portable to community code. There's an extra denote that we consume, but this is again only if it's a hard linked file. So that's the additional cost that we pay there. Then there's some change in the ZIL where we had to handle the additional properties that we are passing in for the hard links, and some changes in the ZFS IOCL. So in summary, we should be able to bring it to community with minimum amount of changes. One part which I guess needs a little more effort is to see how we could extend, or how we could adopt this for the existing file systems. We should be able to bring in the link name hash. We could just populate it on the fly as we proceed, but for the hard links, we don't know if that's feasible. So that part might be tricky, but the rest of it should work. So that's a summary of changes. I think we can open up for questions.